Fabricio is going to speak about the maximum infection time in the geodesic and monophonic convexities.
Okay, thank you. Can you hear me well? Okay, so thank you very much. Sorry about the wrong date, just because I did not have a computer with me in this trip. I had only my tablet, so I could not recompile the file. But Yoshi was kind enough to correct it instantly now. So as you can see, I'm going to talk about actually two different things in this talk. One is the first half of the talk is about convexity problems, and the second half of the talk is about infection problems. And at some point, I'll mention one very particular case of the first kind of problem, which is exactly the same of another very particular case of the second one. So that's why there's this relation between these two guys. I will assume that probably most people, maybe you have background on this topic, but I'll assume I'll start fresh and I'll give all the necessary definitions about both kinds of problems. Then I'll talk about some recent results, some not so recent results, and a few of the ideas involved in the proofs. So let's start from the beginning. So first of all, a convexity for us is just any, I'll only talk about finite convexities. Right? So for a finite convexity, you have a finite set V. And for us, a convexity is just any family of subsets of V, which is the empty set is there, the whole set is there, and it's closed by intersections, right? Maybe you want to call this a different name, I don't know, but the reason why we, or some people call this a convexity is just because in the Euclidean space, if you have like two convex sets, right, and you look at the intersection, this will also be a convex set. But this is just the general definition. That's not how we usually work with these convexities. I'm going to be interested in a very particular kind of convexity, which I call graph convexities. So for a graph convexity, you start with some particular graph G, right, with just some set of, you have some set of vertices, and some of these vertices are connected by edges. And I have my graph G, and I have some family P, and this is a family of paths in G, right? And these paths, they do not need to have any particular properties, just any family of paths, right? Usually, we are going to be interested in particular families of paths. So for example, you can consider all the shortest paths in the graph, but it doesn't have to be like that. You can just pick any family of paths in your graph. And from the graph and the family of paths, we are going to define a particular convexity C. Right? And to define this convexity, I just need to tell you how to test if a set is convex or not. And the way we do it is exactly the same way we do in the Euclidean space. Right? So given some subset of vertices V, we say that this subset is a convex set if for any two vertices that x and y that you pick in S, and for any path in the family that you have chosen, all the vertices from the path that have, all the vertices in a path that has endpoints x and y, it's completely inside the set, right? That's how we usually think about convex sets in the plane. If you pick any two and any path between these two guys, it must be completely inside your set, right? So in this case, we call this particular kind of convexity is a graph convexity. It's easy to check that this thing is closed on the intersection, so that's why it's a convexity. And then, in particular case in which P is the family of all the shortest paths in our graph, we call this a geodesic convexity, right? In the particular case in which P is the family of all induced paths, we call this the monophonic convexity, right? So what do I mean by an induced path in a graph? It's just any path that doesn't have any shortcuts, right? It's some path in your graph in which you don't have an edge between any two vertices which are not adjacent, right? So any induced path, any shortest path is an induced path, but you have induced paths that are not shortest. So in which case your family, in the monophonic convexity, your family has more paths. So this makes harder for a set to be convex, so you have less sets which are convex, right? But then you can look at other families. So you have also the P3 convexity. So in the P3 convexity, instead of looking at all the sets, I look only I look only at paths that have only 3 vertices, right? So it's just I'm looking just at the paths like that in the you have your x and y, and any other path I ignore. It's not in the family, right? And this guy doesn't even need to be a shortest path. So you may have this edge or not, doesn't matter. So I just look at the family of all the paths like that, and I say, okay, with this family, I build my P3 convexity. Right? And in the literature, you'll find many other kinds of convexities. You have the all paths convexity, P3 star convexities, M3 convexity, which we are not going to care about them today, but you can find many papers about each one of those. And when we look at convexities, we have some natural definitions, right, that generalize the usual notions in the Euclidean space. So you have the convex hull of a set S, which is given as, this is the convex hull of S is the smallest set that's convex and that contains S. We say that a set is a whole set if the convex hull is the whole graph, right? And we have this important notion of an interval of a set. So the interval, we think of an interval of 2 vertices has all the vertices which are in between these two, right? So if you have x and y, so the interval between x and y is the family of all the vertices that belong to some path that has endpoints in x and y, and which is in your family, right? And if you know the interval of a pair of vertices, then you can define the interval of any set as the union of all the intervals between any 2 vertices in your set, right? So it contains the whole set together with all the vertices in some path that has any points in your set, right? So in our case, since we are only working with finite sets V, if you want to compute the whole convex hull of some set S, you can do it by just applying the interval function many times, right? Just start with n set S, apply the interval function, then again, until at some point you'll get to the convex hull of the set S. And so people who study convexities in theoretical computer science, they are interested in looking at all kinds of parameters, right? They are crazy about parameters. They define parameters about anything you can think about. So a very natural one is the whole number. So the whole number is the minimal size of a set whose convex hull is the whole thing, right? So given a graph and given your family, you can ask how hard is or how easy it is to find this convex hull, sorry, this whole number. Then there are many others, convex number, interval number, Kara-Teodori number, Hadron number. And since there are so many, why not introduce another one? So I decided to introduce this maximum infection time number, right? And before I can tell you what do I mean by maximum infection time, I want to start my second part of the talk, which is now I'm going to talk about infection problems in general, and then we'll come back to this one. Right? Okay, so about the infection problems, so what do I mean by infection problem? Then again, we have some graph G, and we start with some particular set S0, which is the set of initially infected guys, a subset of vertices. We say this guy is infected, this guy is infected, and this guy is infected. And then suddenly your infection starts to spread in the graph, right? And then it can spread by many different ways. It can spread in a deterministic way or in a probabilistic way. Here we are interested in only in infection process that spread following some deterministic rule. So I fix a rule, and I tell you how I knew vertice will get infected. And the rules in this talk will be only the kind of rules which we call irreversible, because once a guy gets infected, it will be infected forever, right? Once it's dead, it will never become healthy again. Still, again, there are many ways you can the infection can spread. But in any case, I have this family, some chain of sets, which I say, so these guys are the set S0 is the set of elements that are infected at time 0. And then at time 1, some other guys get infected, and then I have some set S1, then some set S2, and so on. So, for example, a very famous or particular rule, which it's basically what we do when we talk about a bootstrap percolation, is that you can fix some parameter R, and you say the infection spreads if a healthy element has some R neighbors which are infected. Right? So you fix some number R at the beginning. You start with your set S0, and then at some time t, who are the guys in ST? It's everyone who was infected before, together with the elements that have at least R infected neighbors. Right? So this is one way some infection can spread, and we call this the bootstrap rule, let's say. And then I'm going to consider now a very different kind of rule, which is I can just use some particular convexity and say that the infection spreads by applying my interval function. Right? So now I have a connection between the two problems. So in this case, so you have your graph G, you have your family of paths P. You start with some infected guys at 0. And then I say, okay, how does the infection spread? If you have this guy is infected and this guy is infected, and you have some path in your family that starts and finishes here, then at next step, everyone in your path will get infected as well. Right? So these are kind of very different ways to spread the infection, right? One is very local. In the first one, you are only interested at your neighbors. And the second one is kind of much more global because it depends. We have a long path starting and ending into two infected guys. But then again, the second one, it will heavily depend on which convexity you are working on, right? And in this particular case, in which we have only the P3 convexities, right? Instead of looking at our shortest path, if I'm going to look only at paths of length 3, then how can this new guy get infected, right? It gets infected if there is a path that has 3 vertices that start in infected guy, finish in infected guy, and only this guy gets infected. But then this is clearly the same thing as the bootstrap rule if you fix r equals 2. Right? Because then this guy will get infected if he has at least 2 infected neighbors. Right? So then I have my very particular problem in this second kind of rule, a very particular problem in which you fix r equals 2 here, and somehow this case coincides, right? So just to give you some fast example, in this case, so let's consider the particular case in which your whole graph is a grid, right? So in the grid, like I think about the vertices in my graph are the whole square, right? So the actual graph that I'm looking at is the dual of that one. So here you have the grid, and then the graph, it's actually this thing. Right. And so the blue dots are my vertices, right? And let's say I fixed the case in which r equals 2. So the neighbors of some vertices are just the guy that it's up, down, left, and right? The diagonal ones are not neighbors. And the red ones, let's say some example in which the set S0 are those red guys. And your infection will start to spread, so you look at some square. If it has 2 neighbors, at least 2 neighbors, 2 infected neighbors, at step 1, it will get infected, right? And then, again, you look at the uninfected guys. If you have at least 2 neighbors infected, it will get infected, and then the infection spreads until, in this case, I will end up infecting the whole thing, which means the original set of red vertices was a whole set, right? So then there are many extremal questions that you can ask about those models, right? You can ask, for example, given some specific set S0, is it true that starting with this set, you will infect the whole thing? Or you can ask, okay, if it does, how long it takes, right, to know? Or what is the maximum or minimum time that it takes to infect the whole thing? Actually, probably the first question, which is a coffee time problem, is what is in the grid, in the n times n grid, what is the whole number in the P3 convexity, right? Which is in the grid, what is the minimal number of infected guys that I can have in order to infect the whole thing? And this is a easy exercise. You can prove that the diagonal, if you just pick this guy, can prove that the diagonal is has the smallest number of vertices to infect the whole thing. And then I think, okay, the diagonal infects everything, but it does so very fast, right? If we start with the diagonal, in time 1, you have the next row, next 2 diagonals. In time 2, you have the next 2, and so on. So in time n minus 1, you will infect the whole thing, right? So our question here is, how slow can you do that? What's the slowest in which you can infect the whole thing, given that you are going to infect the whole thing, right? So that this maximum is not infinity. Right, okay, so here just define the infection time formally. So the infection time, you start with the set as 0, and you just count how many times you need to apply the interval function in order to get to the whole thing. Right, so the general question, it's like that. So given some graph and some integer k, right, I want to know if there is a way to infect the whole thing in such a way that it takes at least time k, right? So I want to know it's a way to formulate the question, which is equivalent to ask what's the maximum infection time on the geodetic convexity, right? Or in whatever convexity you want to look, on the P3 convexity. Right? And we started looking at this question a few years ago, which at the end of my PhD, we started to consider this particular question in the grid. So in the grid for the P3 convexity, we showed that there exists some set of initially infected time, of initially infected vertices, that infect the whole thing in this time, right? This 13 over 18 times n squared. So I want to tell you a little about this proof. So as I said, if you just pick the diagonal of some set, let's see, the n times n, so if you pick the diagonal, the infection will spread, but it will spread very fast. And so the question is, how can I reorganize these guys in a way that it spreads very slowly, right? And by the answer, so the total amount of time that I take, it's quadratic, right? So this means that it should somehow, at each step, you should infect very few guys, just 1 or 2, let's say. Right. This problem, it's a bit counterintuitive because at first you may think that in order to infect the whole thing, I should start with a minimal set. A minimum, you should start with the any infected guys, right? Any infected guys is the minimal amount that I need to infect the whole thing. But the problem is if you have only n guys and you just want to move the position somehow, it's very easy to put them in a position that you end up not infecting the whole thing, right? And this is not allowed. You don't have a lot of freedom to distribute your vertices in the grid, right? So in fact, it happens that sometimes you can have more guys. Right? You start with an infected set that is slightly bigger than n, and you end up infecting the whole thing in a time that's small, slower time than the original ones. Of course, your set must be minimal, but it doesn't have to be minimal, right? So, when we were working on this problem, we had this kind of problems that sometimes, okay, sometimes the most intuitive thing's not true. But anyway, then eventually we end up getting to this recursion, which is slightly ugly, but it's easy. It's easy to show it in the pictures. So if I call MKL is the maximum infection time in a K by L grid. Right? So what's the slowest that you can take to infect the k by k times L grid? We proved that in order to infect the whole thing in the slowest time, what happens in the last step must be one of these 4 figures or rotations of those figures, right? So this means that you infect first this gray area in such a way that the last guy to be infected in this gray area is this white guy. And after, so also this gray area is infected without any help of any vertex which is outside. Right? It's infected only using the vertices which are inside here. And then after you infect this guy, together with this one, the infection will spread. And then to infect the whole thing. And this basically will give you this first term in the recursion. Right? Right? So you prove, so to infect the whole thing in KL, I will first infect the k minus 1 L minus 1 square, and then I'll take some extra time, which is the maximum between k and L minus 1. Right. And then you have these other cases which are analogous. So the first step was to actually prove that one of those things may happen, must happen, which is not so obvious because of the counterintuition in the problem. But then once we do this, we wanted to solve this recursion, right? And at the time, I tried to ask lots of people if there is if any of you know of a general method to solve recursions that have a maximum, this kind of maximum in it. As far as I know, there's no general method to solve exactly. Maybe there is some way to solve it asymptotically. But then we end up with some kind of ad hoc solution that works only for this reduction, but I would still be interested if you know of some general method for trying to attack this kind of guy. What we did was what's like the follows. So we think of each of those 7 cases in your recursion has a direction in which you can grow your rectangle, right? You start with some small rectangle, start with a 2k by 2 rectangle, things like that. And then I say this rectangle is going to be infected in some amount of time. And from this one, I can either add a vertex here, and then it grows to a 3 by k, and I know how long it takes to infect this guy. Or I can add some vertex there. And then it grows to a 4 by k, or it grows in one of those 7 directions, right? And the point is that in each direction, I gain something by growing in this direction, right? And what I gain, it depends on the size of the rectangle that I used to be and the direction in which I'm growing. That's exactly what the recursion is saying. So the point is we can then represent the solution by the sequence of moves that you apply until you get to the whole thing. You start with we start with some k by 2 rectangle, and then I say, okay, I start with this guy, and then from this guy I can apply, say, move 1, and then I apply move 7, and then I apply move 3, move 2, and whatever, until finally I have my n by n rectangle, and just by knowing the moves, I know how long it takes to get there, right? Now, if you look at the sequence, you can ask yourself, okay, what is best to do? Is it true that whenever I have do these moves commute or not, right? Is it true that whenever I have a 1 together with a 7, can I swap and do a 7 together with a 1 and then get a better solution? And then you just do this table with all the possible pairs, right? You have 7 moves, so just do a 7 by 7 table, and you check which of the moves commute. There are some obvious things. So, for example, we immediately see that this kind of move, which my picture is growing, this moves 2, 1, 2, and 3, in which I increase the perimeter only by 2. They are kind of bad, right? And the reason is, if you apply these guys 3 times, if I grow 2 units, and then 2 units, and then 2 units, I end up gaining something like 3 times L, right? It's more or less 3 times L. 3 times L plus 1. While it's much better to just apply this move 2 times, right? Because with this move 2 times, I just grow 3 and 3, and I get and I increase my total amount of time in 4L, right? So we play with this with these numbers. First, we prove that these moves 1, 2, and 3 can be pushed to the beginning of your sequence without increasing the time. And then we end up getting a sequence that has a bunch of 1, 2s, and 3s in the beginning. And then all the moves 4, 5, 7, 6, and 7s at the end. And then somehow we can prove that we can commute these guys as well, and then put only the 2s after only the 1s and after only the 3s. Then when I have the 1s all together and the 2s all together, I do this kind of things of replacing 3 moves 2 by 2 moves 3, and so on. And then we conclude that these moves 1, 2, and 3 are kind of useless, and the important ones are those 4, 5, 6, and 7. But then something interesting happens, right? When we look at these moves 4, 5, 6, and 7, we prove that whenever you have a 6 before a 5, and this is again just by looking at the recursion and apply one and then the other. Whenever you look at the 6 before a 5, this will be bad because you can swap and apply 5 before a 6 will give you a sequence that percolates, that infects everything slower than the original one. So in your sequence, the 5s should always come before the 6. But then we compare the 6 with the 6 with a 4, and we prove that the 4 should always come before the 6 should always come before the 4. But then we compare the 4 with the 7, and we prove the 4 should always come before the 7. But then when we compare the 7 with the 5, we prove that the 7 should always come before the 5. Right? And that's kind of bad, because this breaks the technique that we were hoping for, like just pushing some moves at the beginning and then replace many of them by a single move and then finding the maximum. Then what we do to solve this problem, first of all, we introduce some kind of fractional moves in which we look at a more general version of this recursion, in which instead of adding just 1 and 1 and getting some number, I could, for example, add a half and a half, or a third and a third. And we generalize in such a way in which if you apply many fractional moves, it's the same thing as applying just one integer move, right? If you apply any times this fractional 1 over n move, it's the same thing that applying move 1 only once. And after we have these fractional moves, you can pick any sequence in which you start with some small rectangle and you grow until you're a big one. And any of those sequences that cross the diagonal from 0, 0, 2, and 1, we can somehow reflect in a way that we find another sequence. Unfortunately, this other sequence will use some fractional points in the grid. But then we reflect, we find some other sequence that takes at least as long to infect the whole thing. But this new sequence does not use one of those moves. So it doesn't use move 7, for example. Right? And then, okay, and then we are fine. Now that I have this other sequence that doesn't use this guy, then I break my cycle and I can do as before. Now I know I can push all the 5s to the beginning, all the 6, all the 4. And then I can determine the time to infect the whole thing just by looking at how many times I use the 5, how many times I use the 6, and how many times I use the 4. And then I have some function which we can maximize and find the maximum. And that's how we got to this, right? So this precise number, right? This will be the solution of that recursion for m and n. Okay, so then this was a very particular case, right? Our graph is a grid. Even then, the problem, it's not trivial. There are many things in the grid on this model which are hard to solve. But then we started looking at the question from the theoretical computer science point of view and ask is it possible to find a polynomial algorithm to solve the problem for general graphs or not, right? And those most recent results that we have are in this kind of direction. So the first one was, now you are not in the grid. Now you just have any graph G. So, and the question is, given the graph G and given some parameter K, can you find the maximum infection time? Or is the maximum infection time at least K or not? And we proved that this problem is a NP-complete problem, even if you fix K equals 4, right? So for a general graph, even if you want to decide, can I infect this graph in time at least 4 or not? This is a hard problem in algorithmic way, right? There's no polynomial time algorithm to decide if you can infect the whole thing in time at least 4. Even if you know that your graph is a bipartite graph, when K is at least 7, right? Even if you know that your graph is a bipartite graph, to determine if there is if the infection time takes time at least 7, it's a hard problem. Even if you know that your graph is a planar graph, to determine the maximum infection time is a hard problem. And then we gave for K equals 1 and 2, we gave some polynomial time algorithm. And for K equals 1 is trivial, for K equals 2 is basically trivial as well. And some other people, Marcelon and Sampaio, they closed this gap. So they proved that for k equals 3, there is also some polynomial time algorithm to solve the problem, right? So the problem, it's easy until k equals 3 and hard for k at least 4. And then said, okay, so we have this result for the P3 convexity. So what happens then to other convexities, right? Is the problem easier or harder in other convexities? So also in 2003, there's this group of people proved that in some other, the so-called P3 star convexity, the maximum infection time is also NP complete. And our most recent results are on this geodesic convexity, as I promised at the beginning. And in the geodesic convexity, may say that the problem gets even harder, because even to decide if you can infect the graph in time at least 2 is a hard problem, right? You cannot distinguish. Given the graph, you cannot know if the maximum infection time of your graph is just 1 or 2 in the geodesic convexity. On the other hand, so we also search for some polynomial time results. So for the polynomial time results, we consider some particular class of graphs, since the general problem is difficult. And then for this one, we work in the so-called distance hereditary graphs. So the distance hereditary graphs are precisely those graphs in which the monophonic and geodesic convexity coincide. So it's a graph in which any induced path is a shortest path, right? So if your graph has this property, then then we have an algorithm that runs in polynomial time and which computes the maximum infection time of this graph. The reason why this is nice is because we can kind of use the best of both worlds. So in the geodesic convexity, given some set S, it's easy to apply the interval function of S, right? So given some S, we have an algorithm that computes what's the interval of S. However, in the monophonic convexity, even this guy is difficult, right? Even just given some set S, just to discover what's the interval of this set, it's a NP hard problem. But in the geodesic convexity, we're fine. We can compute this guy. On the other hand, for the monophonic convexity, we had some previous results about characterization of all the minimum Hu sets. And then we use the techniques on these results to find a similar characterization of all the minimal instead of all the minimum. And with these two things, we could put together the algorithm that runs a polynomial time. And I guess just to say, so the basic idea of this algorithm is to do a kind of a decomposition in your graph. So we pick a graph. We pick the graph, and we use the so-called clique decomposition. So we just grab any clique in your graph, which is a set of vertices in which you have all the edges inside. And we use this clique to break the graph into two pieces. There's some piece, something like that. And what happens is that no shortest path can cross this clique from one side to the other. Right? That's the general idea. So if you know how the infection spreads in one side and how the infection spreads on the other side, we can combine and discover how the infection spreads in the whole graph. So we do this recursively, right? Then we look at each piece, break it again, and break it again, until you have some number of graphs which you cannot decompose. And we prove that in these final pieces, any whole set must have only one or two vertices, and then we can just look at all the possible choices of these one or two guys and test all the minimal whole sets and compute the time that each one takes to infect the whole thing. Okay, I had some nice pictures about how this NP completeness reduction works, but I guess I'm almost out of time, so I guess I should skip those guys. So thank you. Thank you very much.
Or comments?